So I will spend about half an hour on previous slides, which you didn't see, I mean previous lecture, and then we will go to a new topic. So one thing which bothered me is the question whether when you say something about a graph polynomial, you really say something about the graph. Okay, and I gave you an example before. If you speak of matrices as one side, like graph polynomials, and linear maps, like graphs, then there are statements about the matrix which say something about the map, like the determinant of the matrix is 0, which means that the kernel of the map is non-zero. Or they don't say anything about the map, like the matrix is triangular, simply because you chose the basis in a funny way, or in a useful way, or whatever. But actually it is equivalent. I mean, so in graph polynomials we also have this notion of semantic equivalence. In linear algebra, two matrices are similar if and only if they represent the same linear map. And here we say two graph polynomials are DP equivalent if they behave the same with respect to graphs. So the question is really, I mean, you may have particular reasons. For instance, in physics, if you have a particular matrix which represents, I don't know what, some fluid dynamic system, then maybe even if you take an equivalent matrix in terms of linear algebra, it will represent a different fluid system. So if the coefficients or the entries in the matrix represent values of a world which you model, then obviously this notion of equivalence is not good enough, because you would have to have it represents the same map plus some parameters are the same. So also in graph polynomials, for some graph polynomials they represent more than just properties about the graphs, like in physics or in chemistry. But obviously if you take two graphs and you put different molecules or different atoms on it, then they are isomorphic as graphs, but they are not representing the same chemical fact. So we are not saying that it is completely meaningless to speak about particular properties of graph polynomials, but you have to have a reason why you want those particular parameters. Otherwise, we say indeed the two graph polynomials are the same if they speak only about the graph. So I was actually searching the literature. I wanted to know what people in the last 50 years have done if they try to do something like this. And it turned out, but this is from a logical or from a mathematical point of view, is purely accidental. The existing graph polynomials have some additional behavior, but which comes from artificial things, like if the cardinality of the vertex set is different, or whether the number of components is different, or people really only wanted to look at connected graphs. So anyhow, we introduce a notion of two graphs are similar if they have the same number of vertices and they have the same number of edges and they have the same number of connected components. But this is kind of arbitrary. I mean, in the literature this happens to be the good choice. But if you have a different reason, you could say, I also want to add the same maximum degree, or I don't know what, depending on your application. But this is definitely something which, in the theory about the Tat polynomial, about the chromatic polynomial, about the matching polynomial, these are the things which people are willing to disregard. So if two graph polynomials behave differently, but only because of the cardinality of the two graphs being different, then they say, well, okay, so let's disregard this case. So we say two graphs are similar if they have the same parameters like this. And then there are quite a few things which are similarity functions, are functions of the graph parameters which are invariant under similarity. And you can have linear combinations of those, and again this will be similarity functions. So indeed this captures something very reasonable, and actually you can characterize all polynomials which are similarity polynomials by building them inductively. It's an exercise, and it's also not very illuminating. So the reason why I introduced this in the papers is indeed because various matching polynomials are not DP equivalent. We have seen the generating and the other matching polynomials are not equivalent, but if restricted to similar graphs, then they are really the same, because the only difference there was the number of isolated points, which you can express in terms of the number of points altogether. And the same about the Tott polynomial. So using this idea, we now say, and this is a bit modified as before, but now we say two graphs usually compared via distinctive power, and we say S distinctive if we restrict to similarity. So two graphs are the same if two graph polynomials are DP equivalent if for all similar graphs, when they give the same value on G1 and G2, and they also give the same value on G1 and G2, the other parameter. Okay, so this is just the same as before, but we have the further assumption that G1 and G2 has to be similar in this sense. And you can do the same definition for multivariate graph polynomials. And then you have the theorem. I won't prove it. You can read. There are slides which give a proof. The proof is one page. But I want to state the property. Two graph polynomials are similarity equivalent. It doesn't matter how many variables they have. Over S. What is S? Where is S? On the previous slide. Okay, so what is this? Oh, S just means similarity, okay. If there are two functions, f1 and f2, which map coefficients or whatever it will be of the graph, so you can compute the coefficients of a polynomial Q by applying the function on the coefficients of the polynomial P plus those parameters, and the other way around. You can recover the coefficients of C by applying the function on the coefficients of Q and the value of those parameters. So, and this definition really fits the literature. Okay. And this is a theorem. I mean, we have a DP equivalence at one side and these functions at the other side. So the theorem really says that if you are only interested in the distinctive power of the graph polynomials over graphs as an equivalence relation, then this is the same as saying you can compute the coefficients of a graph polynomial in this way, in both directions. Now, but this is too rich. I mean, because these f1 and f2 can be arbitrarily crazy. I mean, they don't have to be computable, but they just the proof of the theorem only will state that those functions exist. But obviously, in practice, you are in a much better situation.
So that also implies what we discussed yesterday, that the equivalence of two distinctive power.
No, but but if you take the definition we had yesterday, then you don't need those three values. Okay. So if you restrict it to similarity, then you have to add those conditions. But the point is now, or at least I wanted to know, how would you say a graph polynomial is computable? So obviously you would say, given a graph, there is a computable function which gives me the coefficients of the polynomial, given a basis or something. But it turns out that to have the reasonable theorems, this is not enough. So here is a proposition how I want to say this in a more precise way. So we say a graph polynomial with coefficients in a ring is computable whatever the model of computation is. If the ring allows to speak about Turing computability, then you do it there, otherwise you do it in another model. If there is a function, Cp, which gives me the coefficients of the polynomial, which maps the graphs into sequences of elements of the ring, of corresponding size, which will be, for instance, the coefficients of the polynomial, which is computable. So this function is computable, but you need an additional property. You need a property that, given a polynomial, or rather the coefficients of a polynomial with respect to some basis, the question whether there is a polynomial, whether there is a graph such that computing the polynomial you have in mind really is the polynomial you have found in the forest or whatever, has to be decidable as well. Now in practice, this is usually true. It may be difficult to compute, but it is true. So let's see. So if we do the chromatic polynomial, we know that the chromatic polynomial has a degree which is bounded by some value. Okay? And as a function of the size of the graph. So if you find your polynomial in the forest, you look at the degree of your polynomial, and you say, okay, if there is a graph such that this is the chromatic polynomial, then the graph is not too big. I can compute a bound on the size of the graph. And now I do the most stupid thing. I just try every graph up to isomorphism and compute a polynomial. But this will be horrible. I mean, this will be horrible. But in practice, the second assumption is true. I haven't seen a graph polynomial in the literature with a fixed number of indeterminants where you couldn't guess from the polynomial a bound on the graph. So this is a reasonable assumption. And then you can work with my definition, and we can say the following theorem: two graph polynomials P and Q, which are computable, and they are DP equivalent, then the functions f1 and f2 are computable. I don't tell you how horribly, but at least they are computable. So we start to get a framework on how to talk about graph polynomials, because we want to get somewhere where we say, you know, a graph polynomial is reasonably defined, and when you want to show a theorem that for every graph polynomial there is a DP equivalent other graph polynomial, you want it also to be reasonably defined. So if you have normal forms, you want to say that you have your graph polynomial and I have mine, and they are equivalent, then I want to and yours is nicely defined. So nicely defined will be, it will be computable in this sense, and it will be second order definable. We will go back a bit to these definitions. And then mine should also be computable and second order definable. So we want to restrict the space of all graph polynomials to those which are definable in some reasonable language and are computable in this sense.
For theorem 33, do you need a second property?
I need this property, yes. You look at it will take too much time. But you look, there is a one-page proof of the theorem before, and if you read this proof carefully, then you see that to prove that f is computable, you just need this additional property. It's just putting a puzzle together. Once I've given you the definition, you can finish it yourself. Now, now we can also make something precise, which people use in the literature constantly, but they don't give a precise definition. They say, you know, your polynomial and my polynomial, they are the same up to a prefactor. And this is an excuse. We have seen several versions of the Tat polynomial. This is an excuse to say that all those versions of the Tat polynomial really, in quotes, are the same. But obviously they are not the same. I mean, if you write them down explicitly, they are not the same at all. So here we look at additional definition. We say that P is Q is stronger than P up to a prefactor if the following happens. There are similarity functions, or computable, even you want to say computable similarity function, but this will be easy. There are similarity functions f, which depend on g and the variables here, the indeterminates here, and functions g1 up to gr, where r is the number of, we'll see where it comes, of indeterminates, such that p, this one, can be computed from q by substituting for the variable which appears here, x1, the value of g of y1. I mean, this is a function which gives me again some polynomial, and here also we do all this. So what he says is that actually q and p are the same up to some substitution which only depends on the graph, and you multiply by a prefactor which is a similarity function. And also those substitutions should be similarity functions. And if you look, I mean, this is I propose this definition in our papers, but if you look at it in all the cases where people have argued that my polynomial is the same than yours up to a prefactor, this definition applies. And okay, and here again, so this means the substitution only depends on the size of the graph, on the size of the edge set, and on the number of connected components, and it gives you a polynomial for the graph. It gives you a polynomial which you replace the variable here by the corresponding polynomial. And we say that P is substitution reducible to Q if you have the same relation as here, but this function is the identity. So you only do substitutions here, and F is the identity. And then obviously you can prove under all these definitions that if something is prefactor reducible, then it is also then this is more expressive than this in the sense of dp, and if it is substitution reducible, then it is also prefactor by definition, because f is empty. So we have three notions of reducing or of equivalence, substitution equivalence, or prefactor equivalence, and you see that the matching polynomials are not substitution equivalent, because you need this prefactor, but the prefactor is x to the power number of vertices. So this is exactly what you need here. So now, with those definitions in mind, we can ask ourselves what we mean by semantic properties of a graph polynomial. So the idea is that the semantic property of a graph polynomial is a property which is invariant under dp equivalence, or rather the similarity dp equivalence as I defined now. And then you look at the cases which people prove theorems. So people prove theorems. They say, here is my graph polynomial, and it happens to be that my graph polynomial has the property that the degree of p happens to be the degree of the polynomial p happens to be, say, p, some graph parameter, the maximum degree of the graph. Okay? And they are very happy. This is the first proposition in some paper they publish, and say, you know, my graph polynomial is great. The degree of the polynomial captures whatever it is, the number of vertices, the maximum degree, the girth, the number of connected components. Now I'm saying that actually this is not a semantic property. This is an overshooting of a semantic property. Because the semantic property would be what? The semantic property would be if two graphs have the same polynomial, then they have the same value for this parameter. But if you double the degree here artificially, then they have double the value here, but still the same. So saying that my graph polynomial determines the number of vertices is a semantic property. But saying that the maximum degree of my graph polynomial is the number of vertices is not a semantic property. It's a tool in the proof to prove the first statement, but it's an additional information. It's like in linear algebra. You say, here is a solution of this, a description of the kernel of this linear system. It's not empty or it is empty. How do you find it? Well, you normalize the matrix and then you compute the determinant, which is easy to compute, and therefore you can see it, but actually you only need that the determinant is not 0. You don't care what is the value of the determinant. Okay, so this is a similar situation here. So P, the degree of P equals the value of the parameter P is not a semantic property, but P, the polynomial big P, determines the value of little p is a semantic property. And similarly, you can go on. The number of triangles of G is determined by the characteristic polynomial is a semantic property, but saying that it happens to be twice the absolute value of the third coefficient is not. Because if you if you remove, I mean, it's like if you transform the matrix by something similar, then this property disappears. Okay. Now, why? And you can go on like this. So people in papers very often point out that the definition they gave for the graph polynomial is such that the polynomial is monic. Monic means that the highest leading coefficient happens to be 1. Now this may be nice. I mean, this is to say, you know, I have my linear system and it happens to be that the matrix is already triangular. So this is useful to note, but it's not yet a theorem about the linear system. So here the same, this is not the case. So this is definitely not a semantic property. And now again, if you say the leading coefficient equals the number of vertices, or equal, is not, but if you say that the polynomial determines the value of this thing, then it is okay. Now here is I've shown to you an amazing theorem which said what? It said if you take the matching polynomial in one of the definitions, which is a defect matching polynomial, and you take the characteristic polynomial, then they are equal, literally equal on forests. And this sounds very exciting. But we know that it's kind of an accident, because if you take the other version of the matching polynomial, there is no way of getting the similar theorem. So I analyze this situation, and I look at the following, and I show you this can be produced every time. So what is the clue here? A graph to assume you have two graph polynomials. And assume they happen to be equal on a certain class of graphs, like the forests we had before, planar graphs. Now the semantic content of this just says, it just says that if you restrict your graphs to C, then the two polynomials are deeply equivalent. But they may be different. So the semantic content of this theorem on trees, on forests, just says that on forests, the characteristic polynomial and the matching polynomial, and now you don't care which matching polynomial, have the same distinguishing power, which is still a reasonable theorem. And now we can show that actually the first version is really not a semantic property in the following sense. It can be always achieved. Assume that you have two graph polynomials Q which have the same distinguishing power on a class of graph C. But they're not equal. They just happen to be the same distinguishing power on a class of graph C. Then I can modify one of them, for instance P, and produce a DP equivalent polynomial P prime. And you will later see that actually I can do more. It's not only DP equivalent, it is also computable, and it will also be nicely definable, such that the graph polynomials on C, P prime and Q, really are equal. So what is the meaning of this? It means that the semantic content is the true content, and that the polynomials happen to be equal was a tool in the proof, which is very useful. But the semantic content really says that if P and Q have the same distinguishing power on C, then I can modify one of them within the class of very nice graph polynomials, such that indeed, after the modification, they really are equal. Okay? So this really shows that, and the modification is I don't know, do I have the proof here? No. Yeah, well, this is just to show you that this modification is and actually you just make a case distinction. You say the polynomial is this if it's on C, and otherwise it is this. So you make basically you use that P is equivalent, DP equivalent to Q. So on C you make it equal to Q, and outside of C you don't care, you leave it as it was. So this is a modification which is very minor. It just means that there is a case distinction, and if C is definable in logic, then the case distinction will be definable, and you can do this all. But this is not deep. It's just to illustrate that the distinction between semantic and syntactic properties of graph polynomials is useful, and it has been widely overlooked. You see, in linear algebra, this is standard, that though I'm not sure today the students don't know anymore the difference between a matrix and linear maps. They identify them in a way that they don't realize anymore. But when I was young, we learned linear algebra in Bourbaki style, and we really made the distinction between the linear maps and the representation of the linear maps by choosing a basis and representing the linear maps. But in the whole theory of graph polynomials in the last 50 years, people do all kinds of things, and they when you point it out to them, they say yes, but they still have a feeling that the polynomial which they defined has some unique character, and they don't reflect about the choice of the basis. Now I will switch now, but I can show you still.
In the last proposition, do you have any assumption on the class C of graphs?
Well, it's closed under isomorphism.
That's the only thing.
Yes, and if it is definable, then everything can be done definable, and if C is computable, then everything can be done computable. The trick is really like this: you define P prime of G x equals Q of G x if G is in C, and P of G of x else. And you just have to note that if P was computable and Q was computable, then this will be computable. And it's very stupid. It's a trivial remark.
But then you have to make this to be a polynomial. No.
Yeah, but I have to show you when we go back to the definability of polynomials, we see that we can put this condition can be put somewhere under the summation, and you get a polynomial here. So you have to show, indeed, you are right. You have to show that if this is monadic second or second order definable, and this is second order definable, and this is computable, and this is computable, then this is second order definable and computable as well. This is all. I mean, okay, and this needs some logic, but it's nothing. This is just elementary massaging. The remark is not deep. The remark just wants to explain the distinction between semantic and syntactic property. Okay. Now, okay, I have here some references for you, which you can look. You find them on the side, but actually what I want here these are really three PhD theses which I highly recommend to read. The first two were written under me, and the third one was written under Professor Titman, and they are both very nice expositions of all these topics. Okay, now I have to go. Where is file? Here? Which one is open? This?
Yeah.
This?
Control.
No.
It's closed.
I want to the second lecture. Okay. And we have to go to 73.
73.
There are more or less. Okay. No, actually. Okay, we come back. Now, I have a set of lectures, and I was discussing with Sangil which one we should use today, so we decided not to use it. But I still want to point out this to you. Is there are many papers which talk about the location of the roots of a graph polynomial. I've mentioned to you this before, and I've shown you examples of this statement. And we were wondering, or I was always wondering, is it really reflecting something on the graph? You prove a theorem that the roots of the Cuckoo polynomial are dense in the complex plane. So you show that for every point in the complex plane and for every epsilon, you can construct a graph such that the Cuckoo polynomial has a root in this neighborhood of this point. And actually it's hard work. It turns out to be mathematically a non-trivial statement. And the question is, what does it say? Now, obviously, it says something about the polynomial. So if the choice of the coefficients of the polynomial or the choice of the basis which represents the polynomial has a meaning in physics, chemistry, I don't know, whatever you do, then maybe the location of the root also has a meaning in physics, chemistry, or whatever you do. And actually, yes, this is the case. If you take the location of the roots of the chromatic polynomial, there is a link to phase transitions in some physical system, and the location of the root is an indicator when this phase transition happens. And actually, last time here in Korea, the Fields Medal was given to Smirnov, which actually works about questions like this. So there is a very hot topic here. But it's not about the graph. It's about the graph with something. The coefficients are weights, and the weights have a meaning from physics. Okay. But then, so this is fine. I have no problem with this. But one should say in the introduction that indeed the location of the roots reflects the property not of the graph, but of the graph together with the particular weights which you were giving to model a physical reality. But now I all of a sudden get papers to referee where somebody writes, you know, here is my own Cuckoo polynomial, and there are many papers who study the location of roots of the chromatic polynomial, of the Tott polynomial, of the independence polynomial. Therefore, I want to study the location of the roots of my Cuckoo polynomial. And I had the feeling this is totally meaningless. So I was wondering, how could I prove that it is not a property of the graph? It must be a property of the particular choice of coefficients. So then it occurred to me, and this is what I gave you the definition so far. So if I can prove that my Cuckoo polynomial has location of root somewhere here, okay? And so now you give me your own polynomial, and it doesn't have this. And say, you know, I can massage your polynomial in a way that it is dp equivalent to yours, in a way that it is still computable, in a way that it may be even a prefactor equivalent to yours, and I will put the zeros wherever I want. So obviously this would be a very strong way of stating that the location of zeros is not a property of the graph. It must be a property of the coefficients. And indeed, when we looked at all possible statements of location, the roots are dense somewhere, the roots are, on the contrary, they are not dense, they are all in a disk, which depends only on another graph parameter, like the maximum degree, or whether you want, or if it is local, I can make it dense. And if all the roots are whatever they are, I can make it that all the roots are real by changing bases, but very, very, very minor modification. So we proved that we have a whole paper on this. And then one of the referees said, yes, this is all true and it's all very nice, but it's all dirty tricks. But the answer is yes, it is dirty tricks. It is something people have overlooked. That if the only purpose is that you want to have your graph polynomial up to dp equivalence, and you would like to have the roots wherever you want them to be, then I can produce this for you. You can come to my shop and I will give you exchange your graph polynomial against something equivalent which has this additional property. But this is like saying, you know, every matrix is equivalent, similar to a matrix which is triangular. So triangularity is not, it may be very useful. You have a reason to put the zeros there, to put them there, fine. But it's a theorem like every matrix is equivalent to a triangular matrix. So unless you have an interpretation of the particular coefficients, the location of roots is completely meaningless. And the paper was accepted, actually. It was immediately accepted, and now there was a conference last week or 2 weeks ago in London on recent developments in the Tott polynomial, and I spoke about this, and actually the champion of roots, Sokal, but he proved it really for his physical systems, was there, and he listened to it and he found it also interesting. So well, it just means that if you write an introduction, you want to write a paper about the location of roots of graph polynomials, and you write into introduction, you know, everybody studies roots, I also want to study roots. This is not a good argument in the introduction. You have to have an additional argument why the location of roots is relevant for you. Okay, so that much for this. Now we are... Yesterday we finished actually there are two unfinished business, but somebody, I don't know, asked me, why do you care about definability? Now, first of all, I want to show you how I define polynomials in a logical formalism. And I do care because I want to transfer the theorems which are classically known. If a class of graph is definable in some formalism, then I can say something about the complexity of the decision problem. Then I can say something about the complexity of the computing the coefficients or something. So I want to imitate, I want to transfer all these theorems over to polynomials rather than properties. Yes, Courcell's theory and descriptive, not parameterized complexity, they usually work on graph properties. But if you look in Distel's book, there are very few graph properties which are there, and there are many, many more graph parameters which are there. So I would like to have similar theorems about graph parameters and about graph polynomials. And it is also historically like this. You see, to amuse you a bit, I use this now. In 1995, a student fell from heaven like the little prince in the Technion, and he said he can prove something fantastic. And what could he prove? He said he can prove that random polynomial time equals NP. Now this is a type of theorem, if you come to me, it's almost as good as P equals NP, but it's a little bit less. So if you come like this, I would immediately ask you, do you have a real idea? Otherwise I will dismiss you as, this. Well, so we asked him, do you have a real idea? He said, yes. I can reduce this question to the problem of computing the permanent of a matrix in a field of characteristics 3, and he showed us how he can do this reduction, and it turned out that this was new. He discovered it himself, but it's actually a paper by Papadimitriou and Zachos, which took quite a bit of attention. So this was a good beginning. So then we invited him to do more. And he could do a lot of things. It turned out he was an absolute master of combinatorial linear algebra. He had reduced the problem to some problem on matrices in finite fields and especially permanence. And it turned out that he was the most virtuoso person. I mean, in the Technion we have a few experts on permanence, and he could stun everybody. Turned out also he was a bit schizophrenic and complicated, but mathematically he was sound. And then I wanted to prove a theorem about permanence which he couldn't prove. This is the ambitions of a PhD supervisor. You have a good student, even if he is crazy, you try to say, maybe I still can do something in his field which he cannot do. And then I proved that everybody knows what is the permanent. The permanent is like the determinant but without a -1 in it. So I can prove that I can compute the permanent of a matrix in polynomial time if the matrix is the adjacency matrix of a graph of bounded trivias. And I showed this to him, and you can also do this after I've stated the theorem, but and he couldn't prove it, so I was very happy. And then but it turned out that the proof had nothing to do with permanence, because I only exploited the fact that the permanent can be written as something which is related to the matching polynomial and is related to matching, and you can say it in monadic second order logic and so on. So I had sabbatical in Switzerland, and I met Turayev, who is a leading figure in knot theory and quantum graphs and stuff like this, and happened to be also a semi-relative, I mean, to my wife. They grew up together in semi-relative by in-law. I mean, his father was once married to the aunt of my wife, but they were not. Anyhow, so we met, and I told him, I have this theorem about permanence, but I know it has nothing to do with permanence. It's much more general, but I don't have examples. I mean, I can produce uncountably many examples, but this is funny. I mean, I don't have any other example in the literature. So he looked at it, he listened to me nicely, and then he said, why don't you look at the Jones polynomial? Now, Jones polynomial is in knot theory. I had no idea of knot theory, so I spent a whole year learning knot theory. And then I finally managed to prove that the Jones polynomial can be computed in the general Jones polynomial can be computed in polynomial time on knot diagrams which as graphs have bounded trees. And this was actually an open problem. Somebody even had mentioned this. So I was already very proud. But then again, now I really had a theorem. But then again, I felt after I've understood everything, I felt I didn't use anything of knot theory. I only used the fact that the generalization of the Tott polynomial was definable in a certain way, and I could apply the modified technique of Kurzweil's theorem applied to graph polynomials. So I started to look for more examples where I can do this. So this is from the last 15 years how we developed the theory of definable graph parameters. Okay, so this is just a funny anecdote. But now let's do this. So this is what you have seen before. A graph, numeric graph parameters or whatever they are. You know this already. And now I want to show you slowly, without giving an abstract definition or inductive definition, I want to show you which different point of view I will use to make those things definable in logic. So the first stupid remark, or I mean, everybody could make this remark, but wouldn't realize how this is fruitful. So the cardinality of the vertex sets can be expressed like this. It's the sum of ones where V is a vertex of the graph. So the only thing I have achieved now, I put a term here and I put the formula here. This is an atomic formula speaking about the graph, and this is a term. Okay, so you say, so what? So I say, okay, but I can continue like this. The number of connected components of a graph is a monadic second order definable in the following way. I write again sum over the ones, and here I write that C is a subset of the vertex set, which happens to be a component, and you practice a bit monadic second order logic to say that it is connected. You can say in monadic second order logic. So you have written what I have done from here to here. I still use the same trivial term here, but here I modified the formula from atomic to something much more refined. Now let's do the following. The graph polynomial x to the power of the connected components can also be written like this. How do I do this now? I do it the following way. I write product of x's. How many times do I take? I take the number of elements in the vertex which happen to be, and here is a trick which I want, which happen to be the first element in a component which contains C. So here the formula is actually not in the language of the graph, but in the language of ordered graphs. I give any ordering to the graph, okay, any ordering. When in each connected component I pick the first element, and then I multiply over all those first elements, so I get this expression. Now, but this has an additional interesting property. If you give me the same graph up to isomorphism, but with a different ordering, the value of this expression is the same. So I have used the ordering as an auxiliary tool to climb my mountain, but it doesn't matter where I put the ordering. It's just I have used the order. I need to express it like this, but I have the result of my polynomial is, or the evaluation of the formula is different. If you take all the first elements in a different ordering, you get different elements. But the number of those elements will be the same. It's only the number. It's what you did actually. You added a definable choice function to the graph. Yes, it tells you in every connected component, it tells you how to pick an element. For instance, take the first one. Okay. So
you can also define, I mean, in the second example, you had a set C, right?
Mm-hmm.
So if I replace 1 by x, I still get the...
Yes, you are right. You are absolutely right. But what we will do is, we will allow... you're just one slide ahead. No, but it's very important. It's a very good observation. Here, we will allow summation over subsets or over relations if it's second-order logic. But in the product, we will not. So in the product, we will allow only over elements. So the size of the sum can be exponentially big in the size of the graph, but the size of the products which I'm going to allow to write has to be polynomial. Why? I mean, because it happens to be the case. I mean, you can say, well, you can also allow bigger, but in my formalism, we will do this. We have big sums. This is a big sum. No, this happens to be a small sum because there are only a small number of components. But if you take partial matchings, there can be many, or independent sets, there can be many. So we also will sum over independent sets. We will also sum over matchings. We will sum over cliques or something, where every subset is a candidate. Okay, so sums are allowed to be big, but products will have to be restricted to be small. So, and this is, so you are right. If I had more time or more slides, I would have written, this can be also written as a product over those, which formally is okay because it's still a small product, but it's a small product because of this property, not because of the range of summation. So now I want to show you the difference between monadic and non-monadic. The number of cliques in a graph is definable. You take the sum over all subsets, which happens to be a clique, and you take a one here, where clique says it induces a complete graph. The number of maximal cliques is monadic second-order definable by saying C is a clique, and there is no proper superset which is a clique. However, when you say the clique number, it's only second order but not monadic second order definable. Why? So here I want to do the same. I write down the sum over ones, where C is the largest clique. So C, you take all C's, but it's not just maximal, it's the largest. So there could be another one which is incomparable to it, which is bigger. Okay? So to say this, I have to say C is the largest clique, which means that for every other clique, there is an embedding, but showing, I mean, which compares the size. But the moment I want to compare size, I have to quantify over functions, which is a binary relation. So it is not monadic. So this is monadic second order definable, and you can actually show that this is not monadic second order definable. Okay, so this gives you a flavor of this. And then we give, this is in the thesis of Kotek, we give an inductive definition of those, and then we prove normal forms that do. But basically we give some inductive definition, but then we show as a normal form theorem, every such object can be written as sum, blah, 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 sum, and then product, blah, 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 product, where these may be big sums, but these have to be small products. And the conditions under the summation or product have to be formulas in the whatever logic you want. I mean, monadic second order logic, second order logic. First order logic is not good because for big sums, even if the property is first order, the variable is a second order variable. Okay. So typically the logic we'll have is second order logic or monadic second order logic, and there is a version which Cursor likes very much. It's called counting monadic second order logic. Is where you have an additional quantifier which says d mn x phi of x, the number of x's satisfying phi equals m modulo n. It's a modular counting size. And it turns out that if you extend monadic second-order logic with this counting quantifier, you still get the meta theorems which Kurzweil initiated and other people did. So we have typical fragments for such logic. To me, the main point when we now continue is that such a fragment inherits a quantifier rank from second-order logic. If you write your fragment as a formula in second-order logic, you can define its quantifier rank, and you say every formula has a quantifier rank. This is all I need. So let me do abstract theorems. Okay, this is not. Thank you for your attention. This is okay. So now you have an idea what is second order. You also have an idea. I can give you another example as an exercise you probably need to show you that the difference between order invariant and in general. So we can show the property even, meaning the cardinality of a set is not, we will see in the continuation, not monadic second order definable. However, even is order invariant monadic second order definable. And what do I really mean by this? If you have a naked set, you just have a naked set, then you can use these games, RFC games, and show that if you take a large enough set and then even a larger set with one more element, then the game you can play between the two cannot. You take a formula. You come to me and say, "Hurrah! I found a formula in monadic second order logic, which distinguishes even from odd." And you give me a 200-page description of this formula. Okay. Then I say, I don't have to read your formula. I only have to parse it to compute its quantifier rank, which is easy. And then assume the quantifier rank of your formula is Q. And then I can show you that even plus 1 is or whatever version, or even 2 to the Q and 2 to the Q plus 1 or something like this cannot be distinguished by formulas of quantifier rank Q. So without having to read your formula, I produce you a counterexample. However, now if I have an ordering, I can do the following. I take a relation which says I'm a 2 successor. So this is a 2 successor of this. This is a 1 successor, a 2 successor. And then I say the following. If along the ordering I jump in steps of 2 successors and I reach the last element, then the structure was odd. So the last element is in the transitive closure of 2 successors. But if I have an even structure and I do the same, then I stop here. So I have a formula which says the last element is in the transitive closure of the true successor when I start in the first element. Distinguishes the 2 structures. Okay? And now you say, okay, you cheated, you had an order. I said, very good, give me your own order. And I apply the same formula. Now, on the way of jumping, I will hit different elements. But the property about what happens to the last element remains the same. So this is the guiding example, actually. Even is definable using an auxiliary order in an invariant way, and even is not definable otherwise. So what it turns out is that that I just want to give you an example, which was the kind of a breakthrough. So my version of the Tat polynomial, which is, z of g xy equals sum over A is a subset of E. So this is a second order formula. This is monadic second order in the hypergraph presentation. So G as a hypergraph. So this is in monadic second order logic for hypergraphs. And then I do product of X. I write it first without product. I write it X to the number of connected components of G of the spanning subgraph of A times Y to the cardinality of A. So this we have already seen how to write using order invariant definition. So here I use the product over C is a first element of a connected component of, then I get this, and X here, and here I just write P of Y, V is in A. So we have shown that this version of the Tat polynomial, it's called the partition function of G, is monadic second order definable in the language of hypergraphs using in an invariant way an auxiliary order. Okay, so it shows that the formalism is really not completely cuckoo, but actually it is useful. Here the Tat polynomial can be written like this. And then to prove the theorem I told you, which I proved about knot theory, and which made actually a bit noise, was that I have two theorems. First, I have this one. This gives me the Tat polynomial. Now there is a more complicated definition. To reduce the Jones polynomial, you need a colored Tat polynomial, but never mind. Formally, the trick is similar. It's a bit more difficult, but it's similar. So I have two lemmas or two sub-goals to show that the Tat polynomial needed for the Jones polynomial is monadic second order definable using auxiliary order in an invariant way. And then I can forget about what I have done, that it was the Tat polynomial or the Jones polynomial or whatever. And then I prove a theorem, every such definable polynomial can be computed in polynomial time on graphs of bounded trees. And I got something which really was open. I mean, I was at a conference invited in knot theory, and no, I was invited to the Fields Institute, but there happened to be people in knot theory, and then somebody gave a talk on knots which have a diagram which is series parallel, and then you can compute the Jones polynomial fast. And then I immediately asked, well, if you can do it on series parallel, why can't you do it on 3 with 3 or 4 or 5? And he couldn't do it, and then I managed to do it in this way.
By computing, you mean maybe you choose X to be some number, Y to be some number, then the algorithm give you answer, or do you compute the coefficients as well? Or?
Well, obviously, if I have no, both. I want to extrapolate, so I choose enough values for X and Y to get a grid, and then I fix numbers here, and then I compute the value by dynamic programming for each of those points, and then I use multivariable interpolation to piece the things together. But this is pure numeric analysis. There's nothing to do.
Because the theory of polynomial is known, so.
Okay. So that much for definability. Now again I go out, and how do I go back? The simplest is to close. And then I'm here, okay, and then I go here, very good. No, double click, yes?
Yeah.
Okay. And then Control L. Okay. And now, so now the question is, how do you prove that something is definable or not? So actually, this lecture is almost independent. I want to ask the question whether a property or a parameter or a graph polynomial is definable in some formalism. And I want to show you tools how to prove non-definability or other applications, we'll see. So it will relate to graph polynomials, but the topic is concentrating on something else. Now it turns out that there is a notion called Hankel matrices, or Lovaas has rediscovered it independently and generalized it to graphs, connection matrices, and definability of graph invariance. And there is a paper which has been published by Tomer and myself. So first I want to give you some history, which is actually also cute and is less known. And the history goes like this. Okay, so we will talk, the logics which play a role here when we prove definability will be monadic second order logic with counting, or for any fragment of second order logic which has a quantifier rank. You will see why I need a quantifier rank. So Hankel matrices. If you Google Hankel matrices, Hankel is a German mathematician of the beginning of last century. If you Google Hankel matrices, you find buzzwords like this. So a Hankel matrix is a matrix which can be of finite or infinite size, which has the property that the entry at ij is a function only of the sum. And then there is, now I forgot the name, there is another person who looked at the same thing, but it's only a function of the difference. And they play a very important role in numeric analysis. So we have Pade approximations, orthogonal polynomials, probability theory, coding theory, combinatorial enumeration, but we don't do anything of this. Okay. But this is just, if you Google it, this is what you get. However, in the 60s, very early in automata theory, Schützenberger, Chomsky, and other people, and they looked at the following. We look at words. So what is the sum of two words? It's called concatenation. So we're going to define a Hankel matrix for words by having rows and columns labeled by words. And we say the value inside the matrix is a real number or a rational number or somewhere in a field, but the function only depends on the concatenation of the name of the row and column. So this is a purely formal analog of Hankel matrices applied to words instead of sums. You think of the words as a semigroup, and then the concatenation is indeed the sum of the semigroup. And now this has been used, and the first paper was by Carlyle and Azaria Paz in 1971 in formal language theory and stochastic automata, and it has been completely analyzed, almost completely analyzed, and forgotten and then funny thing is that Professor Paz is at the Technion, and then it was, no, you will see why it is funny, and then it was rediscovered in learning theory by Baimel, Bergadano, Pshuti, Kushilevitz, and two more people, and then further developed, but Pshuti and Kushilevitz are also at the Technion, and Baimel was a student at the Technion. So then all of a sudden it became important again, and actually then it was applied for picture languages, kind of automata on two-dimensional grids. So it has been rediscovered. And really what happened is when Tomer Kotek was doing his PhD, sure. And yeah, one of his examiners was asked me after the exam, but what you do, we called it connection matrix, what you do is reminds me of Hankel matrices, and then we started to look at this more seriously. So what are we going to do? We want to do it for graphs. So now what is the concatenation for graphs? Well, the simplest operation, if you want, but it's usually very useless in combinatorics, is the disjoint union. And indeed, there is a paper in 2007 by Friedman, Lovász, and Schreiber, but the paper is much more important, and this is just a first page observation, which says that a graph parameter is multiplicative with respect to disjoint union if and only if the Hankel matrix for this graph parameter has finite rank and something else. So they started this, but actually then they look at K unions, and K unions are a kind of, and this is why they call it connections. You have a graph, you have a graph, and you have three labeled points A, B, and C, and you have another graph, and we have three labeled points A, B, and C. Let's call them prime, and G1 and G2, and now you do what? You do the disjoint union. But then you can make, there are several versions of this, but it doesn't matter for the theorem. You can just say you identify this point, and you identify this point by equality. Okay? So this is a three connection, and it tells you who connects to whom. And then they have, we will use this notion of connection, okay, by identification. You could also have you add an edge here by corresponding points, but then you don't know what happens to the labels. You want to have the result of the operation should be something which again has three ports. So this is why you identify. But in some cases you can say, you can give any identification scheme, not only A equals A prime and B equals E prime, but you could say A equals A prime and B prime, and these are also identified and things like this. So there are all kind of notions of connections, but we will use only the straight connection. Okay. So this is defined as the K union of two graphs which have K distinguished points. And then what Lovász, Friedman, and Schreiber do, and this is a very, very important new line of graph theory, is they look at partition functions like the Tat polynomial, and they ask when is a graph parameter a special case of a partition function. Friedman is the person who got the Fields Medal for mathematical physics some time ago, and Lovász, I hope you know, and Schreiber is the world champion on optimization, I think, and Szegedy he recently got a European prize of combinatorics. He's a student of Lovász. and they were those three were together at Microsoft, when Microsoft was still making money and using it for sponsoring research. Yesterday they announced the biggest loss in history of Microsoft. This is why I'm saying this. And actually he had a question in physics in mind. And they are good combinatorists, so they worked on this, and there is a book now by Lovas on this. And what they do, I will say you in a moment, that they prove an important theorem which says that basically the condition they put, they say that the connection matrix, so they look at the connection matrix which has a K connection matrix. So you have for a graph parameter P, so you do what? You enumerate all the labeled graphs. Start with an empty graph here, G1, G2, and so. So this is an enumeration of all labeled graphs with K labels. And here in the entry ij, h, you put the value of the parameter P computed on Gi K connection Gj. This is your Hankel matrix or connection matrix for K connections. And now you can have, and the values are in the real numbers, in their case. And then you ask whether a function happens to be a partition function. I won't tell you what it means, but and the answer is the function is a partition function P if and only if two properties. For each K, this matrix has finite rank, and actually the rank can be described as a function of K. And additionally, the matrix is semi-positive definite, meaning that the determinant for every submatrix is positive. The linear form induced is positive. So they found out that these connection matrices are a very, very powerful tool. And actually the theorem in one direction is easy. You can do it in 2 hours in the seminar with all the definitions. And the converse, so if this comes from a partition function, then it has these properties. And then the converse is a very difficult theorem. It uses a lot of algebra, representation theory, and everything. But this put those things into perspective. Now, what we know from my students is that whatever a partition function is, it is definable in monadic second order logic. Okay? So when we looked at this paper in the seminar, we proved that for every graph parameter, not only those which come from partition functions, which is monadic second order definable or counting monadic second order definable, the corresponding connection matrix has finite rank. So I will explain how we do this, but this was the connection. And this was Kotek was my student. Godlin was somebody who is extremely good and refused to do a PhD. I wrote 4 papers with him, very good papers, and I told him, you just have to write down now a text of 100 pages and you'll get a PhD for free. And he said no, because he hates writing, he hates editing. So he refused to do a PhD. No, the reason was also the Technion requires residence requirements. So if you want to do a PhD with me and you come with a finished PhD, this is not enough in the Technion. You have to come to the Technion and do a fixed number of courses and get grades for those courses. And actually this he also didn't want to do. Anyhow, we had this in a seminar, and I just wrote down this theorem, and I knew on my notes it was written that for definable parameters this is always the case, but I couldn't say it after I gave the definitions. Godlin already set up his hand and said, don't you have a more general theorem that for every monadic second order definable parameter you can do the same. So now what can we do with this?
Is the converse true? Right.
Which converse?
Like if it's finite rank, then the converse is not.
The converse is not true. I gave you a paper which shows why.
Oh, okay. All right.
We can produce uncountably many graph parameters which have finite rank. Again, in a stupid way. we construct. If you already ask, let's see whether I could reconstruct it completely. Let's take for disjoint union. Okay. So I will construct uncountably many graph parameters which have all finite rank, actually all have rank 1. What is my parameter? Or even a property, not even a property, Boolean value. So I do the following. I take S a subset of the natural numbers, and I define a property PS of G if and only if G is a clique of size in S. So everybody agrees with me there are uncountably many such properties. Mm-hmm. So let's compute the Hankel matrix of this. So you get all the graphs here because you have the empty graph here. So here you get all kind of values you want. I mean 0, 1, 0, 1, 0 depending on S. And here is the empty graph. Here is the empty graph. And also here you get 1, 0, 1, 0. But every other value is 0. Because a disjoint union of two non-empty graphs is never a clique. So my matrix looks like this. But then I can get this row by multiplying with 0 or so it's rank 2. Mm-hmm. It's again one of those dirty tricks. The paper I give you analyzes this a bit more intelligently and asks how far you can go. But the converse is not true, and it's not true in a very strong sense. So what we ask in the paper I gave you is there a logic which is bigger than counting monadic second order logic for which the theorem about rank is true in some way, and we don't give a final answer, but we push in this direction. Now you tell me when you want to stop. But then, so I said something about fragments. Properties we know, numeric graphing, definability we know. Okay, so here is a question which was actually the trigger for what we did, or one of the triggers. You have seen harmonious colorings. Harmonious colorings is a coloring where each pair of colors is used at most once. So they are actually very stupid. I mean, if the graph is too big, there is no coloring and so on. Now, the fact that they altogether occur in the literature is because Hopcroft and Krishnamurti studied those things in 1982 for some reason in engineering. The paper introduces the motivation, and then it studies it, and it gives some properties about this. So they exist. These are not animals which I invented, but this is an animal which other people invented. Now, I jump here first. Edwards and McDermott showed that computing the harmonious index, which is the minimum colors you need you give me a graph, and I ask what is the minimum colors you need to have a harmonious coloring. And they showed that computing this index is NP hard even on trees. Which for people who work on trees is a very exciting theorem, because here is something which is... So obviously we will know, but now this is a graph parameter, it's not a property. So Kurzweil and my student Rotic and I, we have extended Kurzweil theorem to counting monadic second order definable parameters, and then we would know, and it's easy to see that harmonious colorings can be expressed in this logic, and then it would follow that on trees it should be computable in polynomial time. But we know that this cannot be the case. So it follows that harmonious colorings actually are not definable. Because if they were definable, we could have applied this theorem. So here is a theorem using complexity assumption, which shows a candidate. Harmonious colorings are only monadic second order definable if something terrible happens in complexity theory, or something very good happens in complexity theory, depending on your mood when you get up in the morning. Okay. So, but this is annoying. I mean, non-definability modulo complexity theory and heavy theorems. So we looked at it. So finally, I will give you a hint how this can be done using without complexity. And a similar case is chromaticity. Okay. We want to know whether the chromatic number is not a chromatic polynomial. The chromatic number is monadic second order definable. By the way, the chromatic polynomial is, but the proof is, I give you a proof, which is not the easy one, is two things. The chromatic polynomial can be obtained from this beast by substitution. We'll just do the substitution. And this is monadic second order definable using order. Therefore, chromatic polynomial must be monadic second order definable using order by taking the definition of this and the appropriate substitution. So the chromatic polynomial, but here you don't see how it is definable, but at least you know it is definable. So the chromatic number, so there is a thing which is called the exponential time hypothesis, which says that 3-sat cannot be solved in time a little bit less than exponential, which was first formulated by those three people. And then Fomin, Golovac, Lochstanov, and Sarab proved that assuming this hypothesis, the chromatic number cannot be computed in polynomial time. And then again, we can use our argument, assume the chromatic number was CMSOL definable, then this contradicts this theory. Okay. So even with additional modular counting, the chromatic number is not monadic second order definable.
Maybe you need something, right? Maybe the Fomin's result require that the input is in a graph of bounded click width. Something like that.
Yes.
Maybe there's some
click width.
Yeah.
Click. Yes, you are right. Click width has to be repeated.
Previous is still bounded.
You know, on trees we know it can be computed in polynomial time from this theorem. No?
I'm slightly confused.
Wait, no, wait a moment, I'm confused. Anyhow, here you need click with. The click with is in the paper.
Maybe they are proving that maybe chromatic number cannot be computed in at PT time, where the parameter is click with.
Yes, this is what they do.
Yeah.
Okay. But anyhow, we want to do those theorems without complexity. Okay, now there are a couple of slides. I can go very quickly. So we say a parameter is additive for any box is now any binary operation on graphs. So box is additive, or a parameter is additive for box if you compute it using the sum. It is multiplicative for box if you compute the product. And for disjoint union, we have all kinds of examples which are multiplicative or not multiplicative, or additive or not additive. For instance, the chromatic number and the click number are neither additive nor multiplicative. The number of perfect matchings is multiplicative, and so is the generating polynomial, but the parameter for k matchings is not. The graph polynomials, chromatic polynomial and tot polynomial are multiplicative, and so on. So it's useful to look first if a parameter is multiplicative for something. Then we have also a notion of maximizing with respect to disjoint union, or minimizing. I think there is also some misprint here. That is, instead of this should be minimizing or whatever. But now if you do connection matrix, I've already defined it. Then you have a little observation. If it is multiplicative, then the rank is 1. If it is additive, then the rank is 2. If it is
for the disjoint union.
Yeah, now I do it for the disjoint union. But it will be, if you replace this by any box which happens to be multiplicative or whatever, then it's the same. It's maximizing or minimizing, then the rank is infinite. And to show a non-trivial example is if you take the average degree of a graph as a graph parameter, which gives a rational number, then the rank of the matrix is infinite, and it needs a little twist. This is why I show it to you. You can see that average degree, the matrix is given by the entry number of edges of the first graph plus number of edges of the second graph divided by the sum of number of vertices. And then this, if you are in linear algebra, I learned it when I wrote this paper, so you don't have to be ashamed if you didn't know this, but this is called the Cauchy matrix in the literature, and it's a standard exercise for people who really do linear algebra in applied context, that for every finite matrix, which is a Cauchy matrix, the rank is maximal, and therefore the infinite rank is maximal. So sometimes to show that the rank is infinite may be non-trivial. I mean, or at least, well, for numeric people this is still a trivial argument, but anyhow. So anyhow, just to make propaganda not for me, but for Friedman, Lovász, and Schreiber. So the easy theorem is that f and g are graph parameters with values in an ordered field, and g is not identically 0, then f is additive if and only if g is multiplicative in this form, but g is multiplicative if and only if the matrix has rank 1 and is positive semi-definite. So this shows that you really can do certain things using those matrices. Then I define generalized connection matrices, which you have seen already. And then we can do this for arbitrary graph parameters, which you have. Now here comes the important notion. So far we just played with the notions. Okay. Now let L be any logic. And the only thing I want to know is that the logic is a fragment of second order logic, and every formula has a quantifier rank. Okay. This is all I need. And then I define for a box, for any operation, think of the disjoint union when you read the definition first, but it will be general. So the disjoint union is smooth for the logic L if the following holds. Whenever you have two graphs, two pairs of graphs, I equals 0 or 1, and for two pairs of graphs, G1 cannot be distinguished from H1, or G0 cannot be distinguished from H0, using a formula of quantifier rank Q or less. Then, applying the operation, say disjoint union, can also not distinguish. So you apply the disjoint union or the box to G0, G1, and you apply it to H0, H1. Then if those were not distinguishable before, then also those cannot be distinguished. And then, now it may be sometimes difficult to show that an operation is smooth. Okay? So we'll push the difficulty. If you apply those theorems, I will show you some soft theorems using only this definition. But if in a particular case you say, here is my strange operation, is it smooth for whatever logic it is, it may be difficult to show that it is smooth or not. Okay. But it is not difficult to show that this operation, the connection K, is smooth for CMSI, and also without C. You can also show that the Cartesian product is smooth for first order logic, but not for MSI. Now actually I should ask you, I had an argument with graph theorists. The Cartesian product of two graphs from a universal algebra point of view and from a graph theory are not the same.
But there are too many different definitions in graph theory, so...
Yeah, I got very, no, because I'm a logician, but anyhow, it doesn't matter. So if you have an operation which takes a linear and a linear, and you make the Cartesian product in the graph theory sense, not in the, then you get a grid. And if you do it in the logical sense, you actually get only something like this. But it doesn't matter, both of them are smooth. But for first order logic, not for monadic second order logic. So this definition is not empty. I mean, and it actually has a long history. So here, quantifier-free scalar transductions you can also apply the definition to unary operations are smooth. Quantifier-free vectorized transductions are smooth for first order, but not for monadic second order. Cartesian product is smooth for first, but not for second order. Rich disjoint union is the disjoint union where you add two additional predicates such that you can recover the original sets. So the rich disjoint union is smooth both for monadic second and first order logic. And actually this type of property appears very early in the discussion in the beginning of model theory or the beginning of decidability of linear orders. And yeah, so there are many smooth operations. And this is really the important theorem which we proved, where the one I said before is a corollary, is the following. Let F be a numeric graph parameter, or even a graph polynomial, for any structures, graphs or labeled graphs or hypergraphs, but the parameter has to be definable in a logic which has a quantifier rank. Otherwise I cannot define what is smooth. And let box be a smooth operation for this logic. Okay? So disjoint union and monadic second order logic is a good example to think of. Only under these weak conditions, the connection matrix of this parameter f with this operation box has always finite rank. And actually Lovas, before us, proved that if a graph parameter has finite rank for k unions, then it can be computed in polynomial time on graphs of 3 with at most k. So this was a generalization of Kurzweil's theorem, where you replace logic by finiteness conditions on Hankel matrices.
Nice.
But he only used it for k unions, and we will generalize this even further.
So if you combine this with Lovas's theorem, then you can compute such a parameter when this binary operation is that particular.
Yes. Okay, so I don't know, I'm already approaching time. So I want to give you some applications which are visual, so this will be not very demanding. The proof you can read in the paper, or I mean, it uses a bit of technology, but in the abstract form it turns out to be easy. The difficulty in application will be, you have your favorite logic, for instance, and you want to know, is there any smooth operation? Is there at all any operation which is smooth for your logic? Yes. So I push the difficulty there. But once I know that an operation is smooth, I can run this machinery. So now we get corollaries. The following graph parameters are not monadic second order definable, even in presence of modular counting, and I didn't write it here, and even in presence if you use an order which is invariant. It has to be order invariant, but it will be still the case. Because then you just add the order and you apply the theorem of this to general structures, then you show that that doesn't matter. So here is, this is what I had before, the clique number is not definable. The independence number is not definable. And the chromatic number and the chromatic index, which is the same for edge colorings, are not definable. And also the degree are not definable. Okay, how do we do this? Now, what we do is we will choose the operation in a clever way. No, but you will see that, but I can give you the definition of the clever way. And then we will choose the examples in a clever way. But we don't have to see, look, these are two graphs, and now with a lot of hand waving, I apply Ehrenfeucht-Frey game to show that there is a winning strategy. I will choose the operation in a clever way. I will choose the examples in a clever way. But once I've shown you those, you can really follow the argument to the end. So what do? I take Cartesian product in the sense of not of graph theory but of universal algebra. So Cartesian product looks like this, of linear orders. Okay? I take path, not linear order, but path, just like this. And path has an additional element which is marked black, and an additional element, not an additional, but the first element or whatever, the left element is marked black, and the rightmost element is marked blue. And I take Cartesian product. But then I redefine the relation, the edge relation, in a quantifier-free way. And what I want to say is the following. The edges, this just defines the product. You take the, wait a moment, there is phi. There is one. Anyhow, I take the Cartesian product. So a pair of points is in the edge relation if it is in the edge relation in the first graph and it is in the edge relation in the second graph. And I take an additional edge, and the additional edge is it connects the pair black-black with the pair blue-blue. This is what is written here. It's correct. Okay. So the new edge relation is actually on the disjoint union is given by the Cartesian product in the sense of universal algebra, plus one edge which connects the pair black-black with the pair blue-blue. So now if I take two paths of the same length, I get this structure. And if I get two paths with different length, I get this structure. Okay? So what is the difference between those two structures?
Maybe now you write that
this has a cycle, and this doesn't have a cycle. So we get
and then you show that the Hankel matrix has an infinite rank.
Yes. So then we show that the connection matrix has infinite rank for the property cycle free, for instance. And then this is the visual thing. Now you can look at this in many ways. So we get, for this, we get forests, bipartite graphs, chordal graphs, perfect graphs are all not definable in first order logic because we needed the product, smoothness of the product, and actually we need the smoothness of the product with counting quantifier, which we can prove. I just have to tell you this, but there is a proof of this. Then we get interval graphs are not definable in this way, block graphs are not, and so on. I mean, but you just exploit this by looking at whatever you can do now with cycle free. And you get, here is another example. Now you take trees or connected graphs are not first order definable even in the presence of linear order. You again take the path, you again take the product in the sense of linear algebra, but now you add all those edges, and you write this down in the formula. Okay. And then you look at it, what happens in this case. If n1 equals n2, I get a graph of this form. If n is of this form, I get a graph of this type, and in this case I get a graph of this type. So what is the difference?
connected.
So this is connected, and this is connected, and this is disconnected. So I get n equals 1 equals n2 is a tree, and the graph is connected in this case. So again, I look at the corresponding connection matrices, and I immediately see that the rank must be infinite. So this is very, very cute tool. I mean, and now there are not that many. There are some more. So here we can do what I want to show you. Okay, and then we have, I think I want to stop here, everybody's tired, but you look at those graphs, and I give you exactly what you choose. You get plenty of anyhow, what we do is the following. Let I times P2 be the graph which consists of I disjoint edges in the language of hypergraphs. P2 is just one edge. So, and then you can show that for harmonious colorings, the disjoint union of those things equals at value k. So this is the polynomial at value k. Equals 0 if and only if I plus j is bigger than k choose 2. And you can show that x harmonious is on this graph equals the minimum of those values. There is a parenthesis missing here. And the harmonious, and therefore we conclude that the harmonious polynomial is not monadic second order definable in the language of hypergraphs. Why is this written twice?
One is polynomial, the other is...
One is, yes, thank you. It's difficult when you are close to the blackboard. One is the polynomial and one is the index. Okay. So, and now you can verify yourself. I mean, so, and I don't know any way of, I mean, if you want to play Erfolgreich games in the case of those complicated applications, you will see that this is much harder. So if you go back to my slides, you can play with it. There are many examples, but I've given you the gist of the technique I've explained to you. Thank you.